Here we are given the diagram. It has a pin connection at A. It has a roller at B. I guess it doesn't explicitly say it, but whenever we see that little just kind of ball it's resting on it like at B, that's a roller connection. So you can think of it as just like a ball bearing that's resting on. So it's allowed to move over the ball bearing, but the ball bearing is preventing it from moving in the vertically down direction. And then A, we have a pin there, so it's allowed to rotate at the pin, but the pin doesn't allow it to translate. And we'll get to that when we draw the free body diagram. So what we want here are the horizontal and vertical components of our supports. So we want to know the reactions at A and B. A and B, again, are what we would be considering supports here. We have a pin support at A or a pin connection at A and a roller at B. In the free body diagram step, this is where we have to choose the object of interest that we're going to be isolating and usually removing from its supports. In this case, it's not kind of too complicated to see what our object should be, but what object should we choose to isolate from all of its supports if we're interested in finding what the reactions are at A and at B. The wooden beam is what we can choose as our object of interest. So it's, again, not just a point anymore, it's a whole object. What I'm not including as my object is I'm removing from it the pin and the brackets that support the pin. Those are not in my picture. And the actual roller at B is not in the picture either. It's just the wooden beam is the only thing that's in my picture. I'm going to use a right-handed XYZ coordinate system. We don't care about the thickness of the beam, so I'm just going to represent it as a line here. Now, on the object I chose, I have to put all of the forces and the moments, or the couples, that act on it. So usually I find it easiest with, look at the ones that are what we call external forces or external moments. The ones that are just explicitly defined here, that 500 pounds, and that 600 pound-foot couple. So we have that force of 500 pounds acting, and we know the ratio triangle. And we have a couple acting at the end here of 600 pound-feet. And while I'm here, I'll also include some of the dimensions. So again, the dimension step, we're going to need this like angles that we have on this force, and we need lengths of segments in our object, because when we go to the moment step, we need to know what these lengths are. I've included my external force, 500, the external moment of 600, but what I haven't modeled yet is because I did not include the roller at B or the pin at A, I have to draw in here what the reactions are due to those supports. What were those supports doing to my object that now I can see because I took them away from the object itself? So let's start with the easier one at B. I don't have the roller, so I include what the roller was doing to my object. So for now, we'll go through kind of the full exercise here. We want to think what translation was prevented because the roller was there. So we can think along the x direction, due just to the roller, can the beam move left or right because the roller is there? Right. So again, ignoring the pin for right now, looking just at the roller did allow it to go left and right because it could just roll over that sphere. So it did not prevent that motion, so I don't include a force or a couple. In the y direction, could the beam go up and down because the roller was there? So we know that a roller can only push on our object, so the roller exerted a vertical force, and we know its direction is up. That's not a question. The question is, how hard was it pushing, with what force was that. So we know its direction, and we know it's up, but we don't know its magnitude. So because we don't know it, I'm just going to call that B. Or some cases By, because we know it's the vertical component, but there is no Bx in this case. So one force in the vertical direction, we don't know its magnitude. And because the roller was there, could the beam rotate around the z-axis at that point? Right, so that would be like the beam was here. Could it rotate this way because the roller is there? Right, so it could change its orientation this way. The roller is not going to stop that. So all the roller did was provide one force vertically and specifically in the positive y direction. So that is the reaction that the roller exerted on our object because I did not include the roller in my picture. Now the other support is A. We have that pin reaction. Again, we have a picture of it previously, but we'll go through all the exercises here. At this point A, we want to think, can the beam move left or right when that pin is there? Right, we can't move it left or right. It prevents motion in actually to the left or to the right. So it's not like the roller where we know it can only push. Here, it can't move left nor can it move right. So I could put a force pointing left or a force pointing to the right, and either one would be okay. But when I don't know its direction, I tend to just assume the positive direction. So I'm going to assume it's pointing to the right, and then I'll let the math say if that's right or not. And then we think vertically, can we move the beam up or down because when the pin is there? Right, so it's pinned there, we can't move it up. So because it can't move up, nor can it move down, I have a choice. It could be pointing up or it could be pointing down. I'm going to assume it's up and call that AY. If I assumed AY were down or AX was to the left, I can still get the correct answer. It's just how I interpret my results is going to change a little bit. Positive from a support is going to mean that your assumption was correct. A negative value just means that your assumption was wrong. For something like a pin or a roller, you can't interpret positive and negative like you do for a cable. It doesn't mean tension or compression. It means your assumption was right or your assumption was wrong. So the pin is not going to be in tension or compression. It's just in some direction. And the last motion we have to, again, consider at A is, can the beam rotate at A when it's pinned there? Right, at least a little bit. So here, again, when it's pinned there, we can rotate that beam around the z direction. It does not prevent that, so there is no couple at A. So looking at our free body diagram, we have three unknowns, AX, AY, and BY. In this class, that will most of the time be the case because we can get three equations out of every free body diagram in 2 dimensions. If you have more than 3 unknowns, it's not necessarily wrong because you might have a way of generating more equations, like if there's a spring or something like that. But I would just say take a second look if you have more than 3 unknowns. And also take a second look if you have fewer than 3 unknowns. Again, it's possible there's only 2 unknowns, but just double check it because you want to be careful of that. Now I can write my equations based on my free body diagram. Like we did for particles, this drives our equilibrium equations. The order we do it in does not matter, but I generally like to start with sum of forces and then go to sum of moments. So based on my picture, I want to see what has forces in the x direction. All right, so only considering things that have a force component in the x direction, if I look at the way I drew AX, I assumed it was pointing to the right. So that means that in this equation, it's positive. So all of AX is in the x direction. AY does not have anything in the x direction. My 500-pound applied load, 3/5 of it is going to be pointing to the right. So I have to account for that in this equation. BY only acts along the y-axis. So equation 1, I'm done. I have everything that has an x component. And if I look at it, it only has one unknown, AX. So I'm actually going to jump to the solve step. Because I can solve for AX in equation 1, I will solve for it as soon as possible. I don't have to, but if I'm doing this by hand, it's going to make later steps easier, or it can make later steps easier. So right away, I find that AX is negative 300 pounds. Again, I want to reiterate, this is a pin reaction. This doesn't mean it's in compression. We're not considering compression or tension for like a pin reaction or a normal force. What this means is it actually points to the left. So in our interpretation, we could draw it, we wouldn't say tension or compression, but this is the way that it should actually be pointing. We're done with that. We have one equation. We solved for the one unknown that was in it, so we have to make more equations. I will go to the sum of forces in the y direction next. From my picture, I have AY. I have 4/5 of the 500 pointing down. I have all of BY pointing up. And again, the 600 pound-feet, not in equation number 2. So from this equation, I've introduced 2 more unknowns in the equations, but I've only added 1 equation. So right now I can't solve for AY or BY numerically. So I could solve for AY in terms of BY, but usually I'm just going to put this aside for the moment and go to my 3rd equation. Because if I'm doing this by hand, it's easier if I can get a number for one of these than trying to do this algebraically. But again, the order you do it in doesn't matter too much. So equation 2, it's still a good equation, I'm just not going to use it at the moment. The new equation that we get out now is now we can sum moments around a point, which we did not see in particle equilibrium. Any point we choose in the picture, the sum of moments is going to be 0. So what we want to do, again, we can choose any point, it's going to make a correct equation. What we want to do is choose the one that makes our lives the easiest. So again, thinking about eliminating as many things to write down on the right-hand side as possible, which point is going to reduce the amount of work we have to do the most? Right, if we choose point A, where the pin is, AX is going to pass through A, so it will not appear in the equation. AY will pass through A, so it does not appear in the equation either. As a general rule of thumb, if there's a pin in the picture, that's probably the most efficient point to take the moments about. But again, I want to keep reiterating, if we chose B or if we chose this point, it doesn't have a name, but call it C, we would still get an equation that's correct. It just might be a little bit more work to get to our answer. All right, so I will choose A because it's the most efficient. AX, AY don't appear in my equation. I will have the vertical component of this force, the 4/5 times 500, times its distance, its perpendicular distance from A. Again, if I'm talking about the vertical component, that has a perpendicular distance of 5 feet. And does the vertical component of the 500-pound force create a positive or a negative moment around A? Right, it's going to be clockwise around A, so it will be negative. Remember, we're back to scalar mode now. So around A, that would be going clockwise. The horizontal component of this force has its line of action pass through A, so it will not, I don't need to include it in my equation because its perpendicular distance is going to be 0. Right, so that's taken care of. BY is already vertical. So I have to multiply it by its perpendicular distance to A, which is going to be 10. And is that positive or negative around A? And now this is where I include my 600-pound-foot couple. Just because it's located 15 feet from A, I'm not multiplying it by 15 feet. No matter what point I was taking the moment around, it's 600 pound-feet. So it's 600, but I do have to worry, is it positive or negative around A? Right. In this case, it's clockwise, so it's negative. Right. So those are all the things that contribute to the moment around A. Now in the closing minutes, because I chose point A, this equation only has one unknown in it, by. So I can use equation 3 and solve for by is going to be 260 pounds, positive. This is a normal force. It has to be positive because it can only push. So if we came up with a negative here, something went wrong or it's not a feasible situation. Now that we know by from equation 3, we come back up to equation 2. We plug in the value of positive 260 here. And AY is the only thing we don't know. AY is 140 pounds, also up.